Good afternoon, all. We're going to go ahead and get started. Are we rolling it online? Okay, great. Hope people online can catch it too, and I'll be moderating and answering questions if you have anything along the way. But to all, thank you for joining for today's John and Susan Mathis Distinguished Lecture by Dr. William Tarpeh. I'm Joel Birkin, the Mathis Professor in Civil Environmental Engineering. And John and Susan Mathis have supported S&T for decades and in many ways. In 1995, John and Susan established the Mathis Professorship and supported the department and university in many ways, including their contributions to support this very lecture. However, that commitment is much, much more and much deeper as John shared his expertise, his passion, his time, his leadership to better our department and to better the university in many ways. John Mathis earned his bachelor's and master's degree in civil engineering in 1967 and 1968, respectively, long before environmental engineering programs were common in the U.S., from Missouri S&T, and he went on to found John Mathis and Associates, an environmental engineering firm that was later acquired by Burlington Environmental. John Mathis also was involved in efforts to expand the university's civil engineering department in numerous ways to become the Civil, Architectural, and Environmental Engineering Department, and John was influential in the expansion and redesign of Butler Carlton Civil Engineering Hall around 2000 to 2003. So the Butler Carlton Hall you know today would probably not be in this shape had it not been for John's efforts. He did largely these efforts through serving as president of the University of Missouri Board of Curators and on the Missouri S&T Board of Trustees along the way. And as a result of his efforts and his transformational gifts and transformational efforts to S&T, he was inducted into the Minor Alumni of Influence group in 2021, which, if you don't know, that's about 50 alumni total in about 153 years of S&T. So it's quite an honor to join that group. And that is the highest alumni recognition at S&T. So thank you to John and Susan Mathis. And John is joining us today from Florida. He was unable to be here today and send his regrets. Now to introduce our speaker is Dr. Hunter Schreier.
All right. Yes. Thank you again to the Mathis family for sponsoring the lecture. And I'm really excited to introduce our speaker today. We're in for a real treat. So Will is joining us from Stanford. He's been there since 2018 as an assistant professor in chemical engineering. Before that, he got his bachelor's at Stanford, and in chemical engineering, he went on to master's and PhD at Cal Berkeley, and then postdoc at Michigan with Krista Wigginton and Lou Raskin. Will has received numerous awards, and just a few of them are the Paul Bush Award from the Water Research Foundation, NSF Career Award, the Dreyfus Teacher Scholar Award, and most recently, the MacArthur Fellowship grant. So again, really, that's just some of his many accomplishments. I'm really excited to have him here. And please help me in welcoming Will to Missouri S&T.
Great, good afternoon. Thank you, Hunter, for the introduction, and Joel for the background on the Mathis lecture. And again, John, who's on the phone here for the support for this lecture. As Hunter mentioned, my name is Will, and I am going to talk to you some about my group's work in a broad project that we call Electrochemical Wastewater Refining. It builds on many decades of work on thinking about how to effectively remove pollutants from wastewater, broadly defined, and also then how to make valuable products from those pollutants. I'll tell you a little more about why we call it refining these days, but in short, everything I'm going to talk about today is how to target a given wastewater, target a pollutant in that wastewater, and turn it into a valuable product. Our tools are electrochemistry, so we're going to use electron-driven processes to both separate valuable materials and to catalyze reactions between them. I often like to start with this picture because this is the first wastewater treatment plant that I became aware of as a child. This is now called DC water. Back in the day when I grew up, it was called Blue Plains. And it was something that you could smell from miles away. So I grew up, this is the Potomac River. I grew up just south of Washington, D.C. in Alexandria, Virginia. If you've ever been to the new National Science Foundation office, that's right next to me. That's right next to the movie theater I went to as a kid. But anyway, Blue Plains here was a place that just smelled bad, honestly, when I was a kid in the backseat of cars. And now it's like a world leader in recovering valuable products from wastewater. So I mentioned this to say some of what I'm going to talk about is very much academic and molecular scale, but a lot of it is at least grounded and informed by some of these applications. So to dig in, just make sure. I probably just have to click on it, yeah? That'll do. Great. So I'll give you a few entry points into like how we start to think about the project of electrochemical wastewater refining. One that I find useful is that of planetary boundaries. And so planetary boundaries is a framework that basically says how much can the planet handle across any of these categories. And so these are different categories kind of around the circumference of the circle, like climate change, ocean acidification. And the one we focus on is biogeochemical flows. To orient you to this picture a little more, playing within the bounds of what the planet can handle is in green. If we're just outside of bounds, we're uncertain. It's in yellow. And if we're way out of bounds, we're in the orange color. And so this is some motivation for why we focus so much on biogeochemical flows. You may wonder what this E over MSY is. That's extinction per million species year. That's basically a measure of biodiversity. So we're kind of on par with biodiversity when it comes to these somewhat invisible biogeochemical flows. At least they're out of sight for many of us. So a quote that I love from R. Buckminster Fuller, who's not known for his work on wastewater refining, but he has this wonderful perspective that I really love. I'll let you read it. But to me, what it basically says, or what it means, is that we call something a pollutant or a product not just based on what compound we're talking about, but where it is, right? And so I'll talk at length today about ammonia. And ammonia is a component of fertilizer that feeds over half the world, and bound to nitrogen bound to 3 hydrogen atoms. But when it's in wastewater, it's not just a pollutant, it's a regulated pollutant that we have to get rid of in order to discharge wastewater. Nothing has changed about nitrogen bound to 3 hydrogen atoms. Only where it is has changed and what concentration it is. So if we take that realization, it means that if we resituate ammonia, we can convert it from a pollutant to a product, right? Just by resituating it. In chemical engineering, we would call that separations. So that kind of is how I think about what we can recover from wastewater, is that if we just resituate it and purify it, and I say just, but that takes a lot of work, then it might be, we might be able to change pollutants into products by just changing where they are, so to speak. So for environmental engineers, this is a little bit of old news, but I thought it was worthwhile to say, like, what is environmental engineering trying to do in the next few decades? And so this is a National Academy of Engineering report on grand challenges in environmental engineering. I'll let you read these 5 big goals. So this is like, what should environmental engineers be working on to enhance, to advance what society can do sustainably over the next several decades. And so my take on this, of course, I see the world with wastewater lenses, perhaps, but I see wastewater in all 5 of these, right? So if we're talking about sustainably supplying food, water, and energy, that's hard to do. It's hard to supply clean water if we're not taking care of wastewater. Curbing climate change, wastewater treatment plants emit greenhouse gases by design, and so there are some movements to reduce some of those. Number 3 is sort of like where I live, designing a future without pollution and waste. For those in the environmental engineering field, it's interesting because when we talk about like the regulations that guide our treatment for nitrogen, phosphorus, organic carbon, et cetera, the acronym is NPDES, right? Which is the goal of that was to eliminate pollution. But we've sort of like lowered our horizon on that to say we want to manage pollution. But in some ways, what we're saying about designing a future without pollution and waste is an old call, but just a new version of it. Okay, and then the others in terms of healthy, resilient cities, especially super cities, 10 million people or more, we have to manage 10 million people's waste. And then fostering informed decisions and actions, you'll see some of the life cycle and economic assessment that we do later. So to bring this a little closer to home for me, this is a headline that I did not write, even though by the end of the talk you might think I did. I did not write this, but this was from 2022, and we had an algal bloom in the San Francisco Bay for the first time in multiple decades. And so the powers that be talked about this, and I think the original headline was something like wastewater treatment plants cause algal bloom. And the wastewater treatment plant operators were like, you're kind of throwing us under the bus in a way that's like, we don't make the poop and pee, everyone does. And so this is what happened. But what this meant is that we saw fish kills and a whole bunch of damages that we don't often see in the Bay Area. And so it's really come to the front of mind for people. So I'm going to talk about nitrogen at length. So let's talk about the nitrogen cycle as we know it now. So broadly speaking, we manage nitrogen in a linear fashion. We take nitrogen gas, we fix it to ammonia, N2 to NH3, that's the Haber-Bosch process, and then we apply that ammonia in agriculture. That ammonia makes its way into wastewaters as both ammonia, NH3, and nitrate, two of the most commonly regulated pollutants, and they end up in surface waters. So the ending up in surface waters are these harmful algal blooms or this eutrophication that we see that's more than, it's grown exponentially over the past several decades in terms of these zones around the world. So what is done now is that ammonia and nitrate are converted first to nitrate and then to ammonia, then to nitrogen gas via a process called biological nitrification and denitrification. Nitrification to get all the way to nitrate, and then we partially reduce that nitrate to N2. This is great. It removes these pollutants, right? But we're only doing that to the tune of like 1/50th of the ammonia that we're actually making in terms of the ammonia that gets applied. And so what we're thinking about as a group is a way to turn this line and bend it into a circle a little more by using ammonia and nitrate that are in wastewater to make ammonia de novo that can be used as a fertilizer, a feedstock for chemical engineering industries. And so what we're going to talk about today are two kind of classes of processes. First is reducing nitrate all the way down to ammonia, so doing complete denitrification for the environmental engineers in the audience. In the electrochemistry space, we call this nitrate reduction to ammonia, NO3RR. And then we're also going to talk about recovering that ammonia as a product, right? In short, making ammonia but still being in wastewater is not something that people are interested in purchasing, right? We need to make the ammonia and separate it out. So that's the reaction and the separation that we're going to be talking about today. So it may come across that I'm very passionate about wastewater, and so I'm so passionate that we decided to make a little bit of an atlas, a graphical atlas of wastewater that is by nature incomplete. But we fielded enough questions from chemists and chemical engineers that I thought it would be useful to try to get as much information about different wastewaters in one plot as possible. So if you'll bear with me, this plot has 4 different facts about wastewater. So you see all these pie charts of different wastewaters. So on the x-axis here is the global flow rate, how much of the wastewater there is, okay? On the y-axis is total dissolved solids. You can think about that as just like total conductivity, total salinity, how much is dissolved in the water. And so this immediately gets us like 2 types of wastewaters. In the bottom right here, you have things that are high, wastewaters that are high in volume, but they're quite dilute. They're low in concentration. On the opposite side, you have wastewaters that are low in volume, but high in concentration. Those would be like industrial waters like geothermal brines or produced brines. So immediately we can see sort of this like bifurcation of different wastewaters. So that's 2 facts about each wastewater. Now I'll draw your attention to the top right. That's the value of each wastewater based on its components and what we discharge and what each of those components sells for, so to speak. And then lastly is the components themselves on a mass basis, what elements are present in these different wastewaters. So beyond just being like a fun project to me and telling the world about wastewater, this is useful in at least 2 ways. If you are thinking about an element that you want to recover from wastewater, this tells you which wastewaters are promising mines, so to speak, which wastewaters you should go after. So for example, I'm going to talk about inorganic nitrogen, and so you can immediately see that kind of 3 of these pie charts pop out at you, right? Fertilizer runoff, okay, municipal wastewater, and hydrolyzed urine, right? Because they have big, bright green pieces. That's one way. The second way is that if I have a wastewater, it tells me what I should mine in order, what's most valuable to mine. So you can imagine adding a whole bunch of different wastewaters to this, but this is at least a starting point. So when I say refining, I'm purposely borrowing from like oil and gas refining to say what is, in abstract, what does a refinery do? It pulls in crude oil, a crude feedstock, and we have a bunch of different unit processes on our process flow diagram that generate dozens of valuable products, right? Plastics, fuels, a lot of different commodity chemicals. That's what a refinery does. We're thinking of the same idea, but instead of crude oil, we're talking crude wastewater. And so to know crude wastewater, we need to have a chart like this that tells us what's coming in that day. Is it sweet or sour, right, for the chemical engineers in the audience? And do we need to desulfurize it or not? These types of things. So, and the last thing about refining that I think about is tunability, right? So we need to be able to tune these processes to produce these different products. So both ammonia and nitrate wastewaters, polluted wastewaters, are worth refining. A simple mass balance can tell you that the nitrate-containing waters are lower in concentration but higher in volume. So on the order, these are both around 10 teragrams of nitrogen per year to recover. And then this tunability is important. So oxidation state is something that I'll talk about at length today, but we can also think about physical states, bonding environments, and the product purity as well. So in addition to nitrogen management being linear, we can think about some of the more societal consequences of how we currently manage nitrogen. Environmental, of course, is one. I've talked to you about eutrophication that can be facilitated by our discharge of nutrients like nitrogen and phosphorus. But kind of under the hood of how we manage nitrogen is a bunch of CO2 emissions, right? We use a lot of steam methane reforming to produce the hydrogen that goes into the Haber-Bosch process. So this is a quite environmentally intensive management. And then there's also equity challenges here. There are fewer than 400 facilities where ammonia is produced around the world, which may sound like a lot or a little, I don't know. To me, it's a little considering we have 8 billion people, right? And so this isn't all of them, but you can see that they're concentrated, maybe not surprisingly, in places like North America and Europe, right? So what this means is that someone far away from one of these plants ends up paying a lot more for their nitrogen. So just as an example, illustrative example, someone in Mali in West Africa pays twice as much for their nitrogen as someone in the US, even though the GDP of Mali is much lower. So this is an equity issue, but it's also an environmental issue for all of us because we're paying emissions and energy to basically cart nitrogen around when, in fact, we could do it in a distributed fashion. And wherever there's people, there's wastewater, which means there's nitrogen. So that's some of what we work on as well. So as I wrap up the introduction, just to give you a little more on what we're trying to do, we use the term reactive separations a lot, which means we're combining catalysis and separation. So if we want to go from a contaminant to a product, we need to concentrate that contaminant, convert it into our product, and then purify the product. So I'll show you 3 different processes and sort of the background of them today. In sort of reverse order, I'll show you electrochemical stripping at the end because it's going to tie back into how we purify ammonia that we make. The first thing I'll show you is electrodialysis and nitrate reduction, which is a combined process that allows us to capture nitrate and convert it to ammonia. And then the last thing, the middle thing I'll show you is kind of a combo of all of these where we concentrate nitrate, convert it to ammonia, and purify the ammonia altogether. And why are we using electrochemistry besides the fact that it's exciting, like personally to me? These are some of the benefits, right? It's quite modular. We can integrate it with renewables and do distributed manufacturing. And then we can also replace chemical inputs, especially acids and bases, with electricity. So when I think about a refinery, there's sort of 3 classes of processes that I'm most interested in. One is electrocatalysis. That's what I'll spend most of the time talking about today. This is running redox reactions with electrons, right? And so what I'm showing here is an example of heterogeneous electrocatalysis at a surface. I will also show an example of homogeneous catalysis, which is more in the dissolved phase, like in the bulk water. I won't talk as much today about our work on electrochemical separations like adsorbents and membranes, nor will I talk about our electrochemically mediated conversions, which is when we're producing acid and base that we then use for productive purposes. Again, just to orient us, we're going to talk about nitrogen today. So here's the kind of my take on like the redox ladder of nitrogen. You see all these different forms of nitrogen species, all inorganic forms. And in general, because we have the Haber-Bosch process, all of the products you see here are made from ammonia. We have a great process that produces ammonia, and so we make everything by oxidizing ammonia to different products. What we're thinking about is what if we started with nitrate? Are there any benefits at all? Or disadvantages, right? But we haven't, the reductive pathways are underdeveloped relative to the oxidative pathways by and large. So I'm going to talk about nitrate reduction all the way to ammonia, but some of our more recent work is trying to stop along these reactive intermediates to produce products from nitrate. So in terms of what our lab does is we spend a lot of time on electrochemical processes, we make selective materials, and then we try to translate things out of the lab and into practice. So that's where we spend a lot of time. So for the talk today, like I mentioned, we'll talk in 3 sections, and I'll keep bringing this oxidation state ladder back to you. First, on heterogeneous electrochemical reactive separations, I'll focus on titanium as a catalyst to do nitrate reduction to ammonia. Second, as I mentioned, we'll focus on homogeneous electrochemical reactive separations, and I'll tell you about electrocatalyst in a box. And third, I'll focus on like the highest technology readiness level aspects we have, which is broadening the product portfolio using ammonia that we produce from the first 2 sections. So let's jump into the heterogeneous case. And so one of the challenges of dealing with wastewater is that it's not an ideal feedstock, right? I've told you, like, I love wastewater, we should think about it, but like, there's a reason not everyone's using wastewater. It's not a clean feedstock, right? So a way to concretize that a little more is that wastewaters are dilute and they're impure. So if we look at dilute on this left figure, we're looking at nitrate concentrations from 9 or 10 different sources. I'll say at least one of these is mine, just so that I'm not like criticizing people for things I've done as well. Okay, but in short, if you look at the yellow bar here, that's the common nitrate concentrations in environmental waters, right? We're between like 1 and 10 millimolar. But in the black dots are what concentrations people tend to use in their experiments, right? And so that means if we're doing nitrate reduction and it's a first order reaction, it means the rates we observe are 10 to 100 times kind of too high, right? Because our initial concentration is a little too high. Not a little, it's 2 orders of magnitude too high. But I think about that not as like a horrible thing, but it just means that we've assumed there's a separation that purifies the nitrate, that concentrates the nitrate discharge. Now let's talk about what's impure about wastewater. If I asked you to find the nitrate goldenrod bar in these 4 different waters, you would struggle or you'd have to get really close, okay? And that's because there's a lot of other contaminants in the wastewater, and they rival the nitrate that we're looking for in their mole-based concentration. So we not only have to deal with a dilute reactant, we have to be selective to select that reactant at the catalyst surface or in interacting with the catalyst. So one of the ways that we think about that in the electrochemistry field is we think about what we call the reaction microenvironment, and we need to think about both sides of this interface. So what we can observe are things like the nitrate reduction rate, which we call activity, and the selectivity, what products we make and to what extent. So what the field is most used to thinking about is the structure of the electrocatalyst. What's its chemical composition? How does the crystal structure look? And I'll show you some of those data. What I think is being added to the field now, and as a person who's trained in aqueous chemistry, I think a lot about is what are the properties of the electrolyte, right? How does the electrolyte we use, the liquid that is there, the water, influence what we see? And the big challenge is how do you deconvolute the contribution of both sides of the interface? And by interface, I mean the interface between the solid and liquid here. How do those 2 pieces of the sides of the interface influence the observables, the activity and selectivity? And so we're used to thinking about the fact that this catalyst may change structure through surface restructuring. We're not as used to thinking about, and I'm generalizing here for sure, how the interfacial environment on the electrolyte side changes. So we may have bulk compositions far from the surface here, but they may be very different from the interface here. And that's something I'll show you some data on, but I want to cue you for that already. And so the concept we use here is the reaction microenvironment. Let's look at the interface and go microns or even nanometers in either direction, because that's where the action is actually happening, and that's what we need to characterize. So on the electrode side, I'll just show one slide on this because I want to focus on other things for today. We've looked at titanium foils, okay? And this is a titanium cathode. It's doing a reduction reaction, reducing nitrate to ammonia. And we combine several methods to characterize what's happening at this interface. We combined X-ray diffraction, XRD, grazing incidence X-ray diffraction, X-ray absorption spectroscopy. These are both experimental approaches done at the synchrotron near Stanford. That's called SLAC. And then density functional theory with collaborators through a SunCat Center on interfacial science. And what we were trying to do is figure out what is the active species of the catalyst and what stoichiometry does it have. So we ran several experiments where we changed the potential, that's the driving force for the reaction. The more negative you get, the bigger driving force you have. And then the duration of the experiment to see what species are being formed. And so everything in red is an experiment we did. And then I'm showing you just this little tip of the iceberg of data. This is from the grazing incidence X-ray diffraction. So we're seeing the first 200 nanometers of the titanium cathode here. And on the bottom is the titanium foil without reaction, before reaction. On the top is a titanium hydride standard that has stoichiometry TiH2. And in green is our titanium foil after reaction. Okay, and the black squares here are just peaks that match the titanium hydride. So in short, we've made titanium hydride over the course of the reaction. That's how you see the comparison between green in the middle and red in the bottom. And then we know it's titanium hydride based on what we see here. There's a lot of other work here validated by X-ray absorption spectroscopy and even DFT for like a surface-based Porbet diagram. But suffice it to say that this titanium hydride is the predominant species, and it's developed over the course of the reaction. So moving forward, we wanted to look, like I mentioned, at what's happening in the electrolyte. How does the electrolyte change over the course of the reaction? So to do that, we had some components that we can change, like flow rate of the water and a bulk salinity as a sodium concentration. And then what we were measuring were these observables, if you remember from a few slides ago, the rate of the reaction, and then the selectivity towards ammonia. So the positive and negative signs you see here are like correlations. If it's positive, those two variables vary together. If it's negative, they're inverse of each other. These interfacial properties are ones that are really hard to measure. And so that's what we were after. How can we relate a change in flow rate to a change in ammonia selectivity? And so I'll show you how we were able to both computationally predict and actually measure interfacial pH so that we could explain why when we flow faster, we get less ammonia, we get lower ammonia selectivity as an example. So Elizabeth, who's a former postdoc and is now a professor at University of Kansas, and Jinyu, who's a former PhD student in the group, worked on this with Wilson Smith's group at CU Boulder. And so first we did some computational exercises to look at distance from the interface, the outer Helmholtz plane in particular, and a pH proxy. And you can see as we increase flow rate, we get higher pH, higher interfacial pH, especially in the like 1 to 2 nanometer region. Elizabeth brought this method to our lab and we adapted it to nitrate reduction. It had been done for CO2 reduction. And it's basically in situ infrared spectroscopy. And we used a copper electrode this time and we shoot infrared radiation and we're able to see the first 10 nanometers of the aqueous solution. And I'll show you that when we add a phosphate buffer, basically, to that solution, we can then back out what the interfacial pH is in the first 10 nanometers, which is quite interesting, sure, but useful for engineering as well. So here's some of that data and how we recapitulated these pH relationships. So these IR spectra, these infrared spectra, are showing in different pH regimes the ratios of 2 peaks for the different phosphate species. We chose phosphate on purpose because, not to get too aquatic chemistry, but I would be remiss if I didn't talk about aquatic chemistry. Phosphorus has 3 pKa's, around 2, around 7, and around 12. So we chose it on purpose so that we could get as wide a pH measurement as possible. If I were to show you just these curves on the right, you would say, oh, that's just pKa's, right? Those are the pKa's at 50%. But what I'm actually showing you in addition to those is that we're able to recapitulate those with our experimental measurements of the differences, the ratio of these peaks. So in short, if I have these normalized peak areas, I can back out what the interfacial pH is because I'm looking at conjugate acid-base pairs in the first 10 nanometers of solution, right? And what's absorbed. So that means that I can measure the pH from roughly 1 to 14. If you look really carefully, you'd say, Will, what's happening at pH 4? And I would say every data set has a beauty mark. We just can't quite tell the difference between these 2 peaks. One of them gets too small. But if you told me I could measure interfacial pH at a 10 nanometer resolution with everything besides 1 pH unit, I'd be good. And so that's a fine finding. Okay, now let's put this to use, right? This measurement. And so now we're looking at different potentials and the current density, which is the rate of reaction. That's the white bar, the white curve, sorry. But what I really want you to look at is the coloring, the shading here. So this solution has a bulk pH of 6.5. That's what you measure with a pH electrode, right? A pH meter. But if you look at the shading, you can see that we can get as high as pH 14 in the first 10 nanometers of solution. And this is important because this is what the catalyst actually sees. Now we're talking about the reaction microenvironment. We think the pH is 6.5. That's what we can measure with a bulk measurement. But the pH that the catalyst sees can be as like 12 to 14. That means we're much more proton depleted than we think we are, okay? And that's important because we can use that to our advantage. We can say, well, one, that explains why we get lower selectivity towards ammonia because you need lots of protons to get ammonia. Let me just animate that. Sorry, this reaction here. We need a lot of protons to get to ammonia. So if we don't have many protons, that's why our ammonia selectivity is lower. But we can also see that in looking at these bars, this is Faradaic efficiency, which is an electron balance, basically. In the non-buffered pulsed case versus the non-buffered constant potential, we can triple selectivity. That's what the gray bars are toward ammonia over nitrite. So just by pulsing, we basically turn the light switch on and off, right? We're playing with potential and we're turning it on and off. We're basically allowing ourselves to access a bigger reservoir of protons as we relax the electric field. And for another comparison, the non-buffered pulsed is like having a basic phosphate buffer. So we're kind of buffering, but we're able to just access our protons in solution. So we took all of this and said, okay, let's put this into a process that we can actually use to generate ammonia from nitrate. So the process we developed is called electrodialysis and nitrate reduction. It has 2 steps, so it's like a swing process. First, we feed wastewater into the middle and we do electrodialysis, which is just separation of positive and negative charges from water. And then, now that we have nitrate on the left here, we do our nitrate reduction, but in a protected chamber, right? So rather than doing nitrate reduction in open wastewater where it's dilute and we're looking for a needle in a haystack, we've moved all the needles to one chamber, and now we're gonna do our reaction. And not only that, we'll do our reaction in an electrolyte of our choosing. So we'll choose we'll do experiments to figure out what an optimal electrolyte is, and then make sure our electrolyte matches that optimum in terms of pH and in terms of salt concentrations. So I'm showing the different electrodes here, but the moral of the story here is that we separate nitrate out and then do a nitrate reduction in an environment of our choosing. And so we swing between these electrodialysis, nitrate reduction, et cetera. So we took a lot of the lessons from our reactor design here and applied them. So in our proof of concept is sometimes code language for like, not our best, okay? So proof of concept was our baseline. What could we do? And so those are the parameters we used. I'm selecting a few parameters as an illustrative example. And then we said, okay, let's do better. And so that's our optimized version. We're like, look at this shiny one. We started off not great, but now we're in a better place. But importantly, what we did here is we changed the supporting electrolyte. That's based on experiments I'm not showing right now. We increased the flow rate. That's a lesson from what I showed you earlier. Okay. And then we pulsed our potential. And that's a lesson from what I showed you earlier as well. So now what I want you to do is keep your eye on what changes as we go from proof of concept to optimized, okay? So total current density, a total rate of reaction is much higher, threefold higher when we have our not our proof of concept, our optimized, okay? Same thing with the current that's going towards ammonia. What I really want to show you is this ADA synthesis. This is our efficiency of making ammonia from nitrate. We get much higher and we can convert almost 100% of our nitrate to ammonia over 3 cycles, when before we were doing a measly 25%. Okay? And that's just from these reactor design, very engineering changes, but those are informed by very molecular scale insights. There's not a big change in the recovery because we weren't changing much about that stage. We're optimizing only the nitrate reduction stage. So then we took that and said, okay, let's do this on some real wastewater. So we got some agricultural runoff from a farm nearby, and we actually added more ammonia to it. So it's kind of simulated, it's kind of real. And then we did several batches of 4 cycles each, and then did membrane stripping afterwards to recover ammonia. What we're able to do here is these batches versus their ammonia concentrations. On the left is in millimolar, and on the right is total moles, micromoles of ammonia extracted. You can see we can increase our ammonia recovered by 12x, and this is from a real wastewater, just through these optimization processes. And we did this on purpose with a phosphate buffer so that we could make ammonium phosphate fertilizer, which is a common fertilizer. So what have we done here? We've refined a low-grade, low-concentration wastewater into high-purity reactive nitrogen products. I'm just checking time here. So that we can actually make a valuable product from wastewater. So the lessons from our heterogeneous side here are that we can control the electrocatalyst, the electrolyte, and operating parameters in this sort of like triumvirate way to influence nitrate reduction metrics. I'll next talk about some of our work on homogeneous electrochemistry, which, to be honest, has not been applied to wastewater that much for a variety of reasons. So I kind of see there are like 2 sides of a coin for homogeneous catalysis applied to wastewater treatment. I'll let you read these, but broadly speaking, when I talked to my environmental engineering friends about this project when we first started it, they said, well, that sounds really cute. My friends are honest with me. They said, that sounds really cute. But if I'm being honest, it kind of sounds like you're adding another pollutant to wastewater, right? You're just adding another thing you have to remove, and that other thing has a metal in it, which I'll show you. And I said, that's a fair point. So it prompted me to think more about how are we going to separate out that dissolved catalyst later. And so that's what I'll show you now in terms of this electrocatalyst in a box. So we settled on our first foray into this is this cobalt-centered macrocycle that we call CODIM. And there are 2 key challenges in molecular catalysis for nitrate reduction. First is the separations. That's what I mentioned. If I just put this in wastewater, I would make ammonia, but I'd have a bunch of cobalt in my wastewater. And that's what my environmental engineering friends mean by you've just made the problem worse, not better, right? And then we also need to be able to characterize these reaction rates and mechanisms, but in or adjacent to a real wastewater. So what this looks like is that this cobalt-centered macrocycle gets activated. It gets partially reduced at a carbon-based electrode, a cheap electrode, and then it in turn catalyzes nitrate reduction to ammonia. What we're going to do, the new part, is apply this and study it in a real wastewater, applied to a real wastewater, right? From the chemistry side, most people who study molecular catalysts would say, why would you ever put a molecular catalyst in a really complex water? That just sounds like trouble and like you won't be able to understand what's happening. So with 2 hard audiences to please, we embarked on a journey to do some science that we thought was interesting. And so to be fair, to be clear about how this reaction happens with this catalyst, it's a series of 4 turnovers, so 4 steps, and each step is 2 electrons, right? So we're going nitrate to this nitroxyl intermediate, nitrate to nitrite, sorry, and that's the rate limiting step, to nitroxyl to hydroxylamine to ammonia. So it pairs, it's all the odd numbered oxidation states, 5, 3, 1, -1, down to -3. Okay, I'll show you a little bit of electrochemical data here. And just to orient you, we're going to run several experiments called cyclic voltammograms. We're changing potential, the driving force, the voltage of the reaction, and we're looking for reaction rate measured as a current and peaks that tell us what reaction is happening. So if we're going leftwards, that's reduction, adding electrons. And if we're going rightwards and up, that's oxidation or removing electrons. So here's some actual experimental data. This is with just supporting electrolyte. I put 0 molars nitrate just so that you know that there's no nitrate in this series of experiments. And so what we can see is this is the process of the catalyst getting activated, right? So the cobalt-3 is getting reduced to cobalt-2. And then in this pair of peaks, the cobalt-2 is getting reduced to cobalt-1. So there's two 1-electron transfers that happen to the cobalt center. At least that's the working mechanism. Okay, so now let's actually add nitrate in and see what happens. If we compare, in black is the same CV that I just showed you on the last slide, but we had to adjust the y-axis, and that's current density again versus potential on the x-axis, because now we have nitrate. So we get a lot more reaction happening, and it's negative reaction showing reduction when there's nitrate present. So that's evidence of the actual catalysis. But we see a loss of reversibility, like those two peaks that like match up in the top left. Now it's just like one peak that's more on the reductive part. Okay, and so that's going through several cycles, and that's how we get the turnover. So the electrochemical step here is reducing the cobalt, and then the chemical step is binding the nitrate. Then we reduce the nitrate to nitrite, and then we let the nitrite come off, and we do that several times. So importantly, CoDim interacts with each of the intermediates in addition to nitrate. Okay, so moving forward, what we saw is there are some electrolyte effects here. As we add more bromide, we get less reaction. So that looks like a less negative peak here. And we can look at that for bromide and perchlorate as well. And you can see that the rate is more sensitive to bromide than to perchlorate, right? And so this is just an example that these electrolyte effects matter in the molecular catalysis as well. Okay, so being me, I said, okay, students, let's like throw, not literally, but let's throw some CoDim in real wastewater effluent and see what happens. And I did not expect to see reaction because this is quite a complex water. Like many times so far in my career, and I think many times to come, I was wrong, okay? But what happens with the CoDim is you see the reaction, right? That looks like just like when we added nitrate before, we get evidence of that. So this was in real wastewater effluent after wastewater treatment at the Palo Alto treatment plant. So then we took that wastewater effluent and said, let's see what leads to degradation in activity and performance. Okay, so we said, let's take a simplified wastewater that just has nitrate, basically, has some chloride and sodium too. Then we'll add in inorganic ions to see what the performance looks like there. And then we'll add in organic carbon. Lastly, by that I mean we'll use the real wastewater as well. Okay. So we saw a few things here. If you're looking at, these are the three wastewaters in the different colors, and we're looking at selectivity, Faraday efficiency, again, that's the electron balance, but I want you to focus on the nitrate conversion because you can see this big drop, right? And importantly, the big drop happens between simplified and simulated wastewater, which tells us it's an inorganic ion that's responsible for the performance drop, right? And so that inorganic ion happens to be magnesium, right? So in short, magnesium is depositing on our electrode and inhibiting, and so we saw this via XPS as well. And it's inhibiting our catalyst in some way. And we did this further by doing a series of dosing experiments where we added in, these are rotating disc electrode experiments, but we basically, with time on the x-axis here, we added in a contaminant and saw whether we get a return to baseline when that species is present. And so if you look at the unamended, that matches the calcium and bicarbonate. And so those are all kind of innocuous, right? But the magnesium returns towards zero. That's the inhibition that we're seeing here. And then, again, using that XPS, we were able to see that the uninterrupted doesn't lead to this fouling, but the interruption and allowing magnesium to compete with the catalyst is what really shows the drop in performance. Okay, and then looking back at the aqueous chemistry here, we can say something about what species is most likely to have precipitated here, right? In short, that we see, because we see magnesium hydroxide and not calcium hydroxide, that means our interfacial pH is somewhere between those two values of 9.8 and 12.8 based on the solubility products. Okay, so then moving to a process, we resituated this process goal to say, we don't just want to separate a catalyst from wastewater, we want to separate a catalyst from magnesium in particular, right? We want to separate this cobalt catalyst from magnesium. If I said that to any of my students, they'd say, okay, magnesium is positively charged. The nitrate that we want to go after is negatively charged. Let's use an anion exchange membrane, right? Something that blocks, that lets negative charges through, but not positive charges. So when we do that, what we get is that magnesium, and as the main culprit of inhibition, does not cross this AEM, but nitrate does, okay? And so we get nitrate into this should sound familiar, a protected environment, where our catalyst is sitting. So our catalyst is sitting in a different chamber than our wastewater. We are simply delivering nitrate to it. That nitrate is coming from wastewater. Then we do catalysis in these two connected chambers. We do nitrate conversion now that we've extracted the nitrate. And then we use a gas permeable membrane, I'll show you this a little bit later, to recover ammonia. So there are three steps here. We're extracting nitrate to a chamber where we do catalysis and convert nitrate to ammonia. And then we strip out that ammonia. Rather than stripping it out with distillation, we strip it across a membrane into an acidic electrolyte. So the analogy I make here often is this is like making loose leaf tea, but a far dirtier version, right? It's like the tea is the catalyst, and the catalyst is sitting in like the strainer or whatever you're using. But you can just do this, right? You can just take the catalyst is in touch with the water, but you can remove it, so to speak. But rather than remove it, it's just in a protected chamber. And so this process is one that allows us, it really unlocks a lot of molecular electrocatalysts as long as you can design a process like this. So now let's look at some actual experimental results from this. This is over a 4-day experiment. We're looking at nitrogen concentrations in mass or in mole, whichever you prefer. But in the wastewater nitrate, you're seeing we can get below the EPA limit here. So we're removing nitrate from the wastewater. We're getting nitrate into this cathode chamber, which is where our reaction happens. And then wherever you see a green bar, that's when the electricity is on. And so we then reduce the nitrate to ammonia. And so in those green bars, you see nitrate go down and ammonia go up. TAN is ammonia in the blue. And then you're seeing in the black that we can keep trapping ammonia that we make. So we have a real wastewater. We're extracting the nitrate, converting it to ammonia, and getting that ammonia into the trap chamber. Again, with a real wastewater. Okay, in terms of energy, we're basically, with this process, close to conventional cases of nitrification, denitrification, and Haber-Bosch. Finally, what I want to show you from this vignette is that looking at Faradaic efficiency and nitrate conversion rate, doing ECAB, as we call it, electrocatalysis in a box with real wastewater, we get higher performance than when we did just normal electrolysis, even in a simplified wastewater. So what we're able to do here is, from a real wastewater, have better performance than we had with a simulated wastewater. So a dirtier water, we can do better because of our reactive separation process than with a simple wastewater, as measured in terms of reaction rate and electron balance towards our desired product. So what we've done now is like step this up in terms of engineering. And so this is a bird's eye view of our continuous process. So everything I showed you so far was batch. Now this is a continuously stirred tank reactor. And this we just published late last year. And so now what's numbered as 7, 8, and 9, these are like industrial electrolyzers that we're using to do this process. And we're able to, again, produce real high purity ammonia from real wastewater. So where are we going now? On the chemistry side, we're looking at different metal centers and also different ligands to get to rational design of catalysts to make different products, that tunability that I was so concerned about earlier. We're actually incorporating heterogeneous electrocatalysts into this as well. Like we made it all from molecular catalysts, but turns out saving heterogeneous electrodes from fouling is also a good idea. And then scaling this to actual field level monitoring and treatment. Great, so that's the second vignette, and I'll wrap up with just a couple slides on process engineering to get this back to like the big scale that I started with. So maybe I'm sharing too much, but one of my favorite rooms in my lab is this. I call this the crown jewel of our lab. You might say, why? Glad you asked. It's our dispensing room where we store lots of different wastewater. Okay, so these are all different buckets of wastewater. And so one of the things we're really interested in is recovering ammonia from wastewaters that contain ammonia. There's urine in here. But also, the two processes I've shown you, they make ammonia, and we want to purify that ammonia as well. So we've managed to do this with the process I'll show you on just the next slide from several different wastewaters. These are 4 of them. It's now more like 11 or 12. But we can recover almost all of the ammonia from these different wastewaters using electrochemical stripping. And what electrochemical stripping does is it uses charge and volatility to recover ammonia from different wastewaters. Here's a picture of it in the lab. These 2 reactors that you see, they like fit in my hands. They're like 8 by 8 centimeters in terms of reactor design here. And so we ran this, one of my students, former students, Anna, she ran 2 duplicate reactors for 40 days, about 30, 35, 37 days. She ran them continuously with real hydrolyzed urine that has a lot of ammonia in it. On the left x-axis here, you're seeing removal and recovery efficiency. So we're removing and recovering the vast majority of ammonia. The difference being recovery is what we get in the trap chamber. Removal is just what we get out of the first chamber. And then we're making ammonia to the tune of 20 grams per liter, right? And now we're approaching commercial ammonia concentrations. And so what we've managed to do now is actually play with a swing process again and control what I want you to look at is the distribution between green and red here. This is acidic ammonium sulfate versus alkaline ammonia solution. I won't walk through all the details here, but basically by staggering when we apply the current, we can change the distribution between the 2 types of products, right? The green and pink bars are different heights here. Okay, and then as I begin to wrap up here, one of the things we've just done to move even towards higher practicality, if you will, is actually pair electrochemical stripping with solar panels. Why? Solar panels get efficient, of course, when the sun shines, but they can get too hot and their efficiency can start to drop. Our process depends on ammonia volatilizing from solution, and so the higher that goes, the higher the partitioning out of liquid and into gas, right? And so by pairing our catholyte here with a cold plate, basically running the water on the back of a solar panel, we can win both games. We can cool the solar panel and speed up our process. And so that's what my student Arisa has done, is made the solar panel cooler, the catholyte hotter, and that allows us to produce more power from the solar panel and get more energy efficient ammonia recovery. Here's a picture of Arisa from a proud advisor where we actually ran this outside, and that's something she's doing now. And so what we were doing now is actually scaling this up and out of the lab into like real practice. And so a couple of my former postdocs have started to spin out, have spun out this startup called Recovered Potential. I won't spend too much time on this, but in short, we're scaling up this electrochemical stripping approach. And in the lab, we're still trying to do this on farm as well. And so to get back towards this big picture, looking back at a wastewater treatment plant, this is going back to DC water, where I started on the title slide. So instead of 18 acres of space for nitrification, denitrification, starting with ammonia and getting to N2, we can, in a shipping container, just extract that ammonia out, right? So we're trading 18 football fields for one shipping container that includes balance of plant. And so from a cost perspective, we're quite competitive with some of these improved biological approaches as well. So to zoom out, these are hopefully the three takeaways you're taking from my talk on heterogeneous and homogeneous electrochemical reactive separations, and then thinking about how do we diversify or broaden the product portfolio with ammonia. I'll leave you going back to my favorite figure of the whole talk and tell you we don't just do ammonia, and I think there's a project to do here for not just my lab, but for many labs. I've highlighted areas that we've worked on as a lab, but I think this is like the more the merrier type of approach. If you can think of a wastewater, think of a pollutant and some product to generate from it, then it's worth studying. I talked at length about nitrogen today, but some of the other things we work on are lithium and also other approaches, including sensors and adsorbents and membranes as well. With that, I'll acknowledge my group, and I'm happy to take any questions, and thank you for your time.
Great. We've got an opportunity for questions from the audience, and since we're online, we'll walk around with the microphones.
So the earlier slides you showed with the titanium electrodes and titanium hydride, as I understand, titanium hydride is the catalyst for the. Are there any challenges, issues with the losing the catalytic activity or poisoning of the catalyst, including titanium hydride, maybe some other catalyst in real wastewater?
Good question. Yes. So we have not seen poisoning or drops in activity over the duration of our experiments, but they're certainly not as long term as they would need to be for me to make that statement authoritatively. We've run like for 24 hours max, but what we have seen is that the hydride that forms, that hydrogen can actually go through the lattice. So it can become like a hydrogen absorption type of mechanism, and that hydrogen go through the lattice and then do reactions on the other side, which is quite an interesting phenomenon that like Curtis Berlinget has looked at for other approaches. But we haven't seen poisoning of the catalyst in the duration of our experiments. I can't say it doesn't happen. I just haven't seen it. I haven't run long enough to see it, I think is a better way to say it.
So Jeff Moore and Joaquin Rodriguez Lopez, University of Illinois, for battery purposes, sort of did this kind of redox targeting approach of taking an organometallic and attaching it to a porous, making a porous polymer out of it.
Right. Yeah.
And it seems like have you guys tried to do any of that where you're kind of immobilizing that cobalt catalyst onto a support or part of a support?
Yeah, great question. We have not yet, but we've certainly been like following that work also from like Yogi Surendranath's group and others. They've and even the Smith group, who did a lot of work on this CoDIM catalyst before we came along, they've immobilized it as well. They've seen similar activity, and they've been looking at nitrite reduction in particular. But it's of interest to us. We just haven't really studied it yet. I think there might be some really promising approaches here to have and maybe this is what you were hinting at as well. It's like a flow through, like flow the water and the nitrate through the electrode, and on one side you have nitrate, and on the other side out pops ammonia. So that's sort of like simplifying. That's an improvement over some of our reactor designs that I'm super interested in.
So you are reducing the nitrate to ammonia after the water has been treated to oxidize ammonia into nitrate. Why not apply some kind of thing to directly to the raw wastewater without going through biology treatment to directly recover ammonia?
Yeah, that's a great question, and I can better explain where I see these being applied. So I sort of told the story in reverse, but our lab first started on just ammonia recovery, which is more what you're saying, from the wastewater that has ammonia in it, just get the ammonia out. Why oxidize it and reduce it? We've not recently, but when I first started at Stanford, we started adding nitrate reduction because of nitrate polluted water. Sometimes that's nitrified effluent, but sometimes it's more like agricultural runoff. So not at a municipal wastewater treatment plant. Point well taken. Yeah, at a municipal wastewater treatment plant, the technology we apply is electrochemical stripping, which doesn't do redox on the ammonia. It does water splitting to make acid and base, but it just pulls ammonia out of solution.
I had a question, and maybe I missed it on whenever things were getting, you're having better reactions with the more complicated wastewater. Do you think that's other redox active organics or something in there? Or did I miss something on, is it better selection for the magnesium or something?
Yeah, good question. So when I was showing the electrocatalyst in a box, I showed that our performance is better with our new process in real wastewater than with a standard process in simplified water. I think it's mainly that we're not depending. Part of the reason the Faradaic efficiency is better is that a larger proportion of our anions are nitrate when we've done the extraction first. Before that, you're paying an energy penalty because it's dilute, not quite conductive water.
Other questions? Okay, if not, let's thank Joel has one. Here we go.
So excellent talk, and sorry if I missed it, but within the multiple membranes that are going on here, membrane fouling is probably going to be some type of limitation. Have you observed that, or if you're going to be running this long term, is that one of the limitations and how to maybe get around that?
Yeah, this is a certainly really important question. In every technology I've showed you, there's at least one membrane that is facing real wastewater continuously. So we have observed some membrane fouling. We usually think of pre-treatment as a viable option. So some of that is hardness removal via ion exchange or something like that, or doing electrodialysis early on. So I think that's still an ongoing area of work. We've also tied it to more fundamental work on identifying which foulants are actually most responsible so that we have a more targeted approach. But that's definitely an unsolved problem here.
Do you have any other questions? Otherwise, let's thank Will for his outstanding talk. So keep your eye as you're driving by the wastewater treatment plants for a shipping container with a big solar panel on top of it and just dollars flowing out of it into Will's pocket probably after it's all said and done. Thanks again, Will. And thanks. There was supposed to be food. I'm trying to track down what the... Okay. So stick around just a few minutes and you can barrage Will with other questions as we have the reception.